So now let's take a look at soils. So we're going to kind of break it down here. So we'll look at rocks and minerals, different types of organisms that we have within the soil, organic matter, and then soil pore space and soil water, and how those have to interact just right for soils to better give those nutrients and water and oxygen to the plant. So this is just a visual to show you what soil's composed of. So about 5% of that soil is organic matter, and we're going to do a pretty fun Kool-Aid activity that shows you about organic matter and how important it is to how the little 5% that we have within that soil particle is very important throughout that whole particle. The liquid phase, so different types of liquid that we'll need, obviously water, and then some other types, about 15 to 100%, depending on if we have any rain, if there's been any, if there's been no rain, so about 15 to 10%. We have a gas and air phase, anywhere from 0 to 85%. Mineral matter is about 45%, and we'll look at that more in depth this week in class. So I'm sure you remember from your younger years learning about the three primary types of rock, and those are so essential to the way we view soils and soil science. And so those are really important to know and understand the different types of rocks that we have. So I'm just going to talk through a couple of them, or all three of them, just a little bit. But before we do that, what you need to understand is that the parent material that a soil has, so what it's really formed from, is mostly from rock. So these three primary rocks are extremely important to know, because that's gonna dictate what kind of minerals are within that soil. So first one we're going to look at is sedimentary. Those rocks are, because they're deposited from wind and water, and they're mineral deposits, and then they also become solidified because of pressure. So if they're under any sort of pressure, that is then going to help that rock form, and that's very important to sedimentary rocks. Those rocks also can be in layers, and the sedimentary rocks is really where we can get fossils from, and where we see a lot of fossils. So just some examples that you might know. Shale is a really good one. We have a lot of limestone, sandstone are very good examples of sedimentary. Then we go on into igneous, and obviously igneous is because of any type of really intense volcanic heat, and obviously we know that because of prehistoric times and kind of getting clues from each one of those. But granite's a good example of that. That's a pretty common and popular igneous type of rock, and we'll talk about the different minerals in class this week that igneous has in it, and you'll have to answer a couple questions, I think, this week over igneous minerals as well. Metamorphic is the last one, and we look for metamorphic in more heat and pressure. So that's how it's formed, and some different types of rock that you might be familiar with is like marble. Sometimes shale can also be converted into slate, which we would then it would be considered a metamorphic rock. So within those three rocks, we have 17 minerals that are essential for the plant growth that soil will then need as it forms from that rock. So let's look at some essential elements. This is really important, obviously, because it's these essential elements that we're going to look at are so important for plant growth. They have to have them all to grow. And so we'll look at them more in depth this week, but I just want to talk to you about just a couple of them. So obviously we know that plants have to obtain some sort of carbon, oxygen, and hydrogen from the air and from the other soils, but there are also different types of macronutrients and micronutrients that we see within the soil. So three of the macronutrients that are very important and very commonly talked about, obviously, are nitrogen and phosphorus and potassium, so N, P, and K. But some other macronutrients that are really important are nutrients like sulfur and magnesium and calcium. Some micronutrients that are really important that we have within soils: iron, copper, and zinc are very, very important, but we also have like nickel, chlorine, boron. Those are all very, very important in terms of soil success as well. So you might ask, well, Allison, why do we need nitrogen, phosphorus, and potassium? We've looked at how crops need those, and need NP and K in large amounts. Chlorophyll is really important, and nitrogen helps that function of chlorophyll. Phosphorus helps those nucleic acids, and then proteins, and potassium is really important because of different types of movements and enzymes, stomata movements, and it also helps a lot with the activating those enzymes to make that plant grow. Okay, organic matter. Again, you're going to hear me talk a lot about this because I love organic matter. I love what it does for soils, and I love what it does for plants. So that's just that portion of soil that will include animal and plant residues. So decaying into the soil, very important for not just plant growth, but different types of ecosystems, for different types of wetlands, very important for soil. So what's it composed of? It's composed of carbon compounds, but they're very complex. So what are the functions of organic matter? The first really thing we look at is the sequestration of nutrients. So kind of lining those nutrients up that we just talked about in terms of importance and how it's being used. It's a huge source of nutrients as well. So if we have good organic matter, this is why a lot of people will have a cover crop, or a cheap hay grazer that they'll turn into a green manure and just put it under the soil right before it's matured. It's a really good water storage. It will it's really important for that soil temperature to not be as high. So if you have a 90-degree day for 2 weeks, but if you have that base of organic matter or base of something keeping that soil less than 90 degrees, that's really important as well. We have two types of soil organisms. We have macroorganisms and microorganisms, and both of those are very important for the health of the soil. So we have anything from earthworms to bacteria to different insects to fungi that help the soil, well, in some cases help and hurt the soil form throughout the plant's growing. So my favorite is the earthworm because it does so many awesome things for our soil. And so those, I've just put a couple of those on there. Aerates the soil, gives that soil really good organic matter, and it's going to mix that organic matter from the O layer to the A layer and sometimes the B layer, and it's going to help decomposition happen a little bit faster. So earthworms are extremely vital to the importance for the way we view soils and growth in field crops as well. So here's just an example of what the difference between micro and macro organism is. Obviously macro meaning large, micro meaning small. So you can see different rodents in there, different insects in there, but then you can also see some algae and some fungi in there. So algae, fungi, one-celled organisms, those are obviously microorganisms, and then different things like insects and worms, those are macroorganisms. Okay, soil, water, and soil pore space. So we have, all a pore space is what is occupied by water or air, okay? So in different times of the year or different times of the growing season, that's gonna be different. So right now we're gonna look at the different types of soil water. So gravitational water is really important because that's gonna drain through the soil. So it's not gonna really sit. It's going to try and drain through the soil. Gravitational, so just remember gravity, gravity keeps us grounded, so it's going to go through the soil. Field capacity is really important because that is that water content after that gravitational water has went through the soil. So that's how we can measure gravitation, or that's how we can measure the field capacity of that soil. Okay, so really important when you're dealing, especially with hot summers, or in other cases, big floods. And then permanent wilting point, that is where that soil has reached a level where that plant's not going to be able to come back from. It's kind of flooded that soil pore, so it's going to permanently wilt, and there's not much chances for that plant to come back. So here's what that looks like on a large scale. So you can see the moisture, the pore spaces, and then the water films there. We're going to look at cohesion and adhesion water in a pretty cool lab this week. We'll look at oven-dried wilting point, field capacity, and saturation, but this is a good graphic to show you what the difference between all of those are. So oven-dried is obviously what we would do, you and I would do in a lab type setting, and a wilting point would be obviously from any sort of rain, field capacity the same way, and then saturation just completely flooding that soil pore.